For centuries, humans have looked up at the night sky and assumed one simple thing, that the universe in some form would always be there. Stars were born and died. Galaxies collided and drifted apart. Planets formed, changed, and vanished. But through all of this motion, we believed the universe itself was stable, a vast stage on which everything else came and went. The details might change, but the system would continue. This idea shaped how we think about existence. Civilizations rose and fell, but the universe felt permanent. Even when science told us the universe had a beginning, the Big Bang, many assumed its future would stretch endlessly forward, evolving but never truly failing. But what if that assumption is wrong? What if the universe is not just changing, but slowly, quietly losing something essential, not collapsing in a dramatic explosion, not ending tomorrow, but fading step by irreversible step? At first, the idea sounds strange. After all, the universe is expanding, galaxies are moving apart, space itself is growing larger every second. Expansion feels like growth, not decay. It feels like motion, not exhaustion. Yet in physics, growth and decay are not opposites. Sometimes, expansion is exactly how a system runs out of energy. In everyday life, slow processes are often the most dangerous. A battery doesn't fail all at once. It drains quietly. A structure doesn't collapse the moment it weakens. It erodes over time, and by the time the problem becomes obvious, there is often nothing left to fix. This is why scientists began asking a question that feels deeply uncomfortable. What if the universe is slowly dying, and there is nothing we can do to stop it? This question is not about fear or science fiction. It doesn't come from a single dramatic discovery or a secret experiment. It comes from decades of careful observation, measurements of distant galaxies, the behavior of energy, and the fundamental laws that govern time itself. To physicists, the concern is not whether the universe will end, but how it behaves as time moves forward. Does it recycle its energy? Does it maintain balance? Or does it steadily lose the ability to create structure, motion, and change? Because if the universe is losing that ability, then its future is not a mystery waiting to be solved. It is a process already underway, and this matters more than it seems. The fate of the universe determines the fate of everything inside it: stars, galaxies, planets, and even the laws of physics as we experience them. No technology can reverse it. No civilization, no matter how advanced, could escape it. This is not a problem to be engineered away. It is a condition of reality itself. Scientists care about this question not because it threatens humanity tomorrow, but because it defines the limits of existence. It tells us whether time has a direction, whether complexity can survive forever, and whether the universe has an unavoidable end state. And the most unsettling part is this: the universe does not appear to be slowing down or stabilizing. In many ways, it seems to be accelerating toward a future where less and less is possible. If that is true, then the universe is not heading toward a dramatic finale, but toward silence. So the real question is no longer if the universe will change. It is what stage of that process we are already living in. For most of modern scientific history, our understanding of the universe was built on a surprisingly comforting idea that while things change, the overall system remains balanced. Stars burn their fuel and die, but new stars are born from their remains. Galaxies collide and merge, yet structure continues to form. On the larger scales, the universe appeared to behave like a self-sustaining process, dynamic, evolving, but not fundamentally fragile. This picture made intuitive sense. After all, the laws of physics seemed stable, predictable, and reliable across vast distances and immense spans of time. At the heart of this understanding was the idea that energy is conserved. In simple terms, energy can change form, but it is never truly lost. Light becomes heat. Motion becomes friction. Matter converts into radiation. Even when stars explode or black holes form, physics tells us that nothing essential disappears. Everything is accounted for. This principle became one of the strongest foundations of modern science, allowing physicists to describe the universe as a system that transforms rather than depletes itself. The Big Bang Theory reinforced this view. It told us the universe had a beginning, a hot, dense state from which space, time, and matter emerged, but it did not necessarily imply an end. For a long time, scientists debated whether the universe would expand forever, slow down, or collapse back in on itself. In all of these scenarios, the assumption remained the same: the universe was governed by timeless laws that would continue to operate indefinitely. The details of the future were uncertain, but the framework felt solid. To make sense of this vast complexity, scientists often used simple metaphors. The universe was compared to a machine running according to fixed rules, or to a cosmic engine converting energy from one form to another. Even as entropy, disorder, increased, it was thought to do so in a controlled way, leaving room for structure, motion, and change far into the future. Time, in this picture, was simply a parameter that moved forward as events unfolded, and for a while, this model worked remarkably well. It predicted the behavior of planets, stars, and galaxies with astonishing accuracy. It explained nuclear reactions in stars, the formation of elements, and the large-scale structure of the cosmos. Every new observation seemed to strengthen confidence that we had captured the universe's essential mechanics. But even within this success, there were quiet assumptions. One of them was that the universe as a whole was not running down in any meaningful sense. Yes, local systems could exhaust their fuel, but on the largest scales, the universe itself was assumed to be resilient. Expansion was seen as a neutral process, space getting larger, not weaker. Time passed, but the rules remained unchanged. This is why the early cracks were easy to overlook. Certain measurements did not fit perfectly. Some behaviors required additional explanations. Dark matter was introduced to account for missing mass. Dark energy was proposed to explain unexpected expansion. Each time, the framework was adjusted, and the universe still appeared manageable, understandable, and stable. But beneath this familiar picture was a growing realization: the universe might not be behaving like a perfectly balanced machine. The assumptions that once made everything feel secure were starting to show limits. And those limits raised a troubling possibility that the universe is not merely evolving over time, but steadily losing the conditions that make structure, complexity, and change possible at all. The shift in how scientists began thinking about the universe did not come from a single moment or a dramatic announcement. Instead, it emerged slowly through a pattern that became harder and harder to ignore. As astronomers looked deeper into space and further back in time, the universe did not behave as expected. Measurements of distant galaxies revealed something deeply counterintuitive. The expansion of the universe was not slowing down, it was accelerating. According to classical gravity, all that matter and energy should be pulling everything back together, or at least resisting expansion. But the data showed the opposite. The farther away a galaxy was, the faster it appeared to be moving away from us. This discovery forced scientists to introduce a new concept: dark energy. Not because it was fully understood, but because something had to account for this unexpected behavior. Dark energy was not observed directly. It was inferred from its effects, like a force built into space itself, pushing everything apart. And unlike familiar forms of energy, it did not dilute as the universe expanded. It remained constant, growing more influential as space grew larger. This alone raised serious questions. A universe dominated by such an energy source behaves very differently from the balanced system scientists once imagined. At the same time, another long-standing principle began to take center stage: entropy. The second law of thermodynamics states that in an isolated system, entropy tends to increase. In simple terms, usable energy spreads out and becomes less available to do work. While this law had always applied to stars, engines, and everyday systems, scientists began realizing it also applied to the universe as a whole. Over time, energy becomes more evenly distributed. Differences in temperature, density, and motion slowly disappear. And without those differences, nothing interesting can happen. What made this realization unsettling was the scale. The universe is not just experiencing local increases in entropy. It appears to be moving toward a state where energy is so spread out that stars can no longer form, reactions can no longer occur, and structure itself becomes impossible. This outcome, often referred to as heat death, is not an explosion or a collapse. It is a quiet ending, a universe that still exists, but can no longer change in meaningful ways. The problem is that these ideas were once considered distant, almost philosophical, but modern observations suggest the process is already underway. The accelerating expansion driven by dark energy means galaxies will eventually move beyond each other's observable horizons. Light from distant stars will never reach new regions of space. Each cosmic neighborhood will become increasingly isolated, cut off from the rest of the universe. Scientists did not expect these processes to align so neatly. Expansion, entropy, and energy loss were once treated as separate concepts. Now they appear to be reinforcing each other. Expansion increases isolation. Isolation limits interaction. And limited interaction accelerates the spread of entropy. The universe is not simply getting larger, it is becoming less capable of producing complexity. What makes this especially challenging is that none of these observations are easily dismissed. They come from multiple, independent lines of evidence: supernova measurements, cosmic background radiation, large-scale structure surveys, and fundamental physical laws that have been tested countless times. Each piece fits uncomfortably well into a picture where the universe is drifting toward a state of exhaustion. This is where the old framework begins to fail. A universe that endlessly recycles energy and structure cannot easily coexist with one that accelerates apart while steadily losing the ability to support change. Scientists are not panicking, but they are forced to confront a possibility that once seemed unthinkable: that the universe is not merely evolving through different phases, but following a one-way path toward a final, irreversible condition. Faced with the growing evidence that the universe may be running down rather than maintaining balance, scientists have not settled on a single explanation. Instead, they have outlined several possible futures, each grounded in known physics, yet each deeply unsettling in its own way. None of these possibilities are certainties. They are frameworks for understanding where the observed trends might lead if the laws of nature continue to behave as they do now. One of the most widely discussed possibilities is known as heat death. In this scenario, the universe continues to expand. Stars slowly burn through their nuclear fuel, and energy becomes increasingly spread out. Over immense spans of time, temperature differences disappear. Without hot and cold regions, without pressure gradients or energy flows, nothing can happen. No new stars form. No complex structures emerge. The universe does not collapse or explode. It simply reaches a state of maximum entropy, where change itself becomes impossible. Scientists consider this outcome because it follows directly from well-tested thermodynamic laws. The difficulty is that it predicts a universe that technically still exists, but is functionally inert, a place where time continues, but nothing meaningful occurs. Another possibility is sometimes called the Big Freeze, closely related to heat death, but driven more strongly by cosmic expansion. As dark energy pushes galaxies farther apart, each region of the universe becomes isolated. Eventually, distant galaxies slip beyond the observable horizon, their light stretched so thin it can never be detected again. From any given location, the universe would appear increasingly empty. Stars would die out, leaving behind cold remnants like white dwarfs and black holes. Even these remnants would slowly lose energy. Scientists take this scenario seriously because accelerating expansion is not speculative, it is directly observed. The challenge lies in predicting how dark energy behaves over extremely long timescales, something current physics cannot yet do with certainty. A more speculative, but profoundly disturbing possibility involves something called vacuum decay. According to quantum field theory, what we perceive as empty space may not be in its lowest possible energy state. It could be metastable, stable for now, but capable of transitioning to a lower energy state under the right conditions. If such a transition were to occur, it would propagate at the speed of light, fundamentally altering the laws of physics as it passed. Particles, forces, and structures as we know them might simply cease to exist. Scientists consider this idea not because it is likely, but because it is allowed by current theories. The unsettling part is that there would be no warning and no way to observe it coming. There is also the possibility that our understanding of energy itself is incomplete. Some physicists suggest that what we call dark energy may change over time, or that the universe could lose usable energy in ways not yet accounted for. In this view, the universe's decline is not driven by a single mechanism, but by subtle effects that accumulate over billions of years. This possibility is considered precisely because so much of the universe's energy content remains mysterious. The limitation is obvious. Without a complete theory, predictions remain uncertain. What unites all of these possibilities is not their details, but their direction. Each points toward a universe where complexity becomes harder to sustain, where structure fades, and where the conditions that allow change gradually disappear. Scientists do not agree on which outcome, if any, will occur. But the fact that so many independent ideas converge on a similar theme is difficult to ignore. The universe may not end in fire or collapse into darkness. It may simply run out of opportunities for anything new to happen, and that realization forces us to confront a reality where the ultimate fate of the cosmos is not dramatic destruction, but quiet exhaustion. As we consider the possibilities, from heat death to vacuum decay, a larger question emerges: what does this mean for the universe, for life, and for humanity itself? It is not a question with immediate answers, but it is one that frames the context of our existence in profound ways. The universe, vast and ancient, may not be a timeless stage on which events play out indefinitely. Instead, it may be a system with limits, slowly approaching a state where change, complexity, and even the emergence of new structures become impossible. In this perspective, everything we see, stars, galaxies, planets, and even life itself, exists within a finite window of cosmic opportunity. The awareness of that window is both humbling and motivating. For humanity, the implications are subtle but significant. Civilization, technology, and even our understanding of physics are temporary constructs operating within a universe that has a lifespan dictated by fundamental laws. While our daily lives are largely unaffected, the big picture reminds us that the universe is not under human control. No matter how advanced our science or how ingenious our engineering, we cannot reverse cosmic expansion or halt the spread of entropy. Our actions may shape life on Earth, or even on nearby planets, but they cannot alter the trajectory of the cosmos itself. This awareness forces a perspective shift. The universe is not merely a backdrop, it is a dynamic entity, and we are fleeting participants in its vast, ongoing processes. Yet, within this sobering reality lies profound meaning. Knowing that the universe is constrained encourages deeper inquiry, richer observation, and more careful reflection. It is why scientists continue to study dark energy, measure distant galaxies, and explore the subtle mechanics of fundamental particles. Understanding the universe's trajectory does not grant control, but it grants knowledge, a kind of intellectual participation in a process far larger than ourselves. Science becomes a way to engage with the cosmos, to map its behavior, and to anticipate what is possible within its limits. The fate of the universe also invites philosophical reflection. If change is finite and complexity temporary, then the present moment gains significance. Stars shine, planets rotate, and life emerges within a delicate window that will not last forever. From this perspective, every discovery, every act of observation, and every effort to understand is a way of participating in a fleeting cosmic narrative. We may not be able to prevent the ultimate decline, but we can bear witness to the richness of existence while it is still possible. This is both a humbling and inspiring thought. The universe's limits do not negate meaning, they shape it. Finally, the future of the cosmos remains an open question. Observations continue. Theories evolve. Dark energy may behave differently than expected. Unknown physics may intervene. Yet even in the face of uncertainty, one conclusion is clear. The universe is not static, and its ultimate fate is a question that extends far beyond the human timeframe. It is a question that demands patience, curiosity, and a willingness to confront reality without illusion or wishful thinking. So, as we close this exploration, the universe does not offer final answers. It offers perspective, wonder, and a challenge to understand it as it is, to appreciate the fragile window in which complexity exists, and to continue seeking knowledge in a cosmos that is vast, dynamic, and slowly, inevitably changing. The universe didn't give us answers, it gave us better questions. And in those questions lies both our humility and our opportunity to witness the extraordinary process of existence unfolding.